axial load here, you have some sort of curve like that. It's very complicated. But you know that if you make enough distance compared to that point, that means L is enough large, then this curve is going to converge to a curve, right? Uniform. That means the value of the stress, which is dF divided by dA, sigma at any point. So if you consider the infinitesimal dA, there is an infinitesimal force there called dF, right? dF divided by dA, sigma. This value is same across this entire section. So if this is the concept of when I say average stress, I'm actually talking about the average value per this section. So another form of elemental, we can always show that there is an average stress for any cross section. In order to show that, I say, well, let's consider the infinitesimal element here, right? What is the force applied to this point? That dF, according to the definition we have, is equal to sigma at that point times dA, right? Now, this is not average stress. This is stress at any point, which is defined according to this equation. See, stress at any point is dF, that point divided by dA, right? Now, if I integrate both sides of this equation over this entire area. Now we go to calculus 2. Area. Integrate over area. What do I get? Summation of all little forces. Infinitesimal forces. What is the summation of all these little forces here? It will be equal to the net resultant force, which is P. So that's going to end up with P is equal to what is the integral of the variable function, assuming that this could be, well, if it's, of course, if it's uniform, then we get sigma bar times A, right? If it's uniform, it's equal to constant times area. But even if it's not uniform, there was a theorem in calculus 1 that say mean value theorem that says you can write any function as y bar times delta y. The analogous form to that, it says that if you take integral of sigma dA that is equal to average, like average function, times A. Right? The area of that cross section. This is a theorem we had in the calculus 1. So I'll just use it here. So in order, instead of that, I can always write sigma bar times area. For any non-uniform stress distribution, I can find the average stress. But it's not accurate near this point. It's not fair to say the stress is average equal to at any point, because here there is a significant amount of stress at the center, but nothing here. But it is very accurate here, because sigma average is equal to the stress that we measured at many of those points. So this is one concept. This is page 327. And there is another thing that I want to say is, if you consider an element, let's say you take a two-dimensional element right here, like that. This is in your book, and I want to explain it, because when you read it, it looks a little bit crazy. So, that is the element. Let's draw it a little bit larger than that. So I zoom over that little element right here. So here you you have a force in this direction, which is our axial force, it's obviously a sigma, right? Sigma was for the axial load, tau was for shear stress. This axial stress, shear stress. Now if I make my x, y, z this way, x, y, z, right? Then I'm going to have a sigma, and because this is in the x direction, I say sigma sub x. And here at this point also, I'm going to have a stress, because I may have, if you have a load like that, let's say put another 200 pound here, this way. And let's say put another 200 pound this way, right? Then I would have some component of force in this direction that cause and kind of stress, right? Kind of stress. We call this tau or shear. So this is normal stress. This is shear stress. And it's because if this is applied in this axis, in this plane, this is plane X, right? And it's toward Y direction, so you put sub X to Y. In fact, sigma X, if you just take tau, it's tau XX. So in the graduate course, you see everybody just saying tau, there is no sigma. And tau is a matrix. I'm going to talk about it in a moment. And everything here is like tau XX, tau XY, tau XZ, and blah, blah. Everything is tau. In fact, this normal stress is also tau at this plane X toward X. So the first subscript is plane. The second one is direction. But for a special case of repeated indices, XX, we say sigma X, that means normal. If you have repeated indices, it means it's normal stress. Then this one is, you are in plane X because it's X, right? And then you are toward Y, so you have XY. What about this component of the stress here? Thank you, tau XG. Now let's go to this plane. This one. This is plane 1, Y. So therefore, you have a component like that, component like that, component like that. What kind of a stress is that? YY. Tau YY, which is, we call it normal stress, because it's double indices. Sigma Y. Sigma X, sigma Y, that's a normal stress in the Y direction, normal stress in the X direction, and we're going to have a normal stress in the Z direction. So what about this guy? This is going to be tau Y, Z, tau Y, X. And finally here, this is tau ZZ, sigma Z, and then this is tau ZX, tau ZY. Now you can you will be able to understand this thing that the book does, because it doesn't explain why this terminology came. The first subscript is the plane, the second one is the direction. And if you have double subscript, repeated subscript, then it's normal stress. So what happens here, we see that we have how many stress components do I have with just simple loadings? I'm going to have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So with the simple loading, I'm going to have 9 stresses. How many of these stresses have we covered so far? 2 of them. Just normal, simple shear, right? But this happens in 3D. So if I can put it in a matrix, this information, tau XX, tau XY, tau XZ, tau YX, tau YY, tau YZ, tau ZX, tau ZY, tau ZZ. So this main column, we can call it also sigma Z. sigma y, sigma x. That's my shear stress matrix. They call it tensor. But in the graduate course of elasticity, you don't have matrix. You have either a scalar or vector or tensor. Tensor is generalization of matrices. So what happens, this matrix is symmetric. That means this is equal to that. Tau xy is equal to tau yx. Now I will highly recommend, because I want to keep this as a midterm waiver opportunity, I highly recommend to read to read page 36. Page 336, and there is a simple proof for that. Why this is symmetric, why this is equal to that. Y tau xz is equal to tau dx. Y tau yz is equal to y tau zy. It comes from rule of equilibrium, right? And you are able to understand that. So maybe next class or maybe in 2-3 classes, when it comes to opportunity, then I say if you can prove that or some sort of relation related to that, if you can show it on whiteboard, then you don't do midterm. Opportunity for midterm value, right? So now we go to next section. Next section, already gone over there. Now we want to do some more examples. Let's go to page. Example. Okay, it says find the average stress. So when I say average stress, I'm talking about the region here, right? Because when you get to near this point of connection, you get the stress concentration. It's kind of point of singularity. I'm talking about this region, right? Find the average stress in this region and in this region, from AB to C, BC. So what should I do? Well, according to the definition of average stress, I need force and area. Area is just readily given here, so I need force. How do I find the force? Basic vector studies. So I just say the first thing system. Which one is my system? The lamp. This is the lamp. 80. Here we go. Then next step is FED. So if I draw FED for that, I'm going to have F, B, C, and F, H, D. This is 60. This has the ratio 4, 3, 5. And there is the gravitational force, or body force 80 times 981. perfectly in the Y downward, right? FAB and FBC, the ratio is given now. This all I have in FED. Now the next step is write equation and then solve and verify. Don't forget, the question says these two are bars, they are not cables. Otherwise you can have negative force, compression. Although this evidence that you only have tension, right? But when it say bar, you got to be ready. If you have negative values, you should accept it. So here, my x-axis is this, default x, default y, obviously. So I write summation of function x, 0, and give me FBC times 4 over 5, positive, and negative FAB, cosine 60 is equal to 0. Summation of y0, that will give me FBC times 3 over 5 cos FAB times sine 60 negative 18 times 981 0. And what was summation of moments? 0. You know 0 is equal to 0. So it's valid, but I don't write it because it's not going to help you. It's just waste of time. 0 is equal to 0. So how many equations do I have? How many unknowns? Can I solve it? The answer is yes. And well, obviously, FAB is equal to, put in the calculator. Well, here, first, you actually, FBC, FAB. Let's solve one of them for the other one and substitute to get the other one. So here, well, you can substitute here. So FBC times 3 over 5 plus FAB, which is 8 over 5, FBC times sine 60 is equal to 80 times 981. Calculator 80 times 981 divided by FBC is equal to 395.2 Newton, if the units are Newton. Yeah. And then from here we can get FAB, multiply that by F, multiply that value by 8 divided by 5, 6, 3, 2, 0.4. Please double check on the results. So then we say, according to the definition of average normal stress, is equal to the force in that section divided by area. Now we come to this section from A to B. What is the force in that section? FAB, so we say sigma average in AB. But when I write that, you know that it's not exactly from A to B. It's from somewhere that becomes uniform, probably here, to somewhere that becomes uniform here. Here are just the stress concentration, according to the discussion that we had before. So it's from here to here, right? It's equal to FAB divided by area AB. Cross-sectional area here. So if I draw that in 3D, it's like that, right? So the cross-section diameter is equal to 10 mil. So I say FAB, which was 632.4 Newton divided by the area here, which is pi times diameter divided to 10 to negative 3 squared. Put in calculator, 6. Like 8.5 megapascal from here to here. So if I want to draw my actual, my normal stress, or actual stress, or normal stress, most of them are saying, from here to here, what kind of curve should I write? Let's say this is normal stress, this is my average, and this is my x. In fact, you remember the curve we drew that last time? I'm kind of rotating to fit this member. So what kind of curve is it? Positive, this positive, this negative, and this 0. Where should I put it? Positive. So all the way from here, and what you know that not exactly at this point. From here all the way to near this point is positive 8.5 mega Pascal. Sigma, I'm not saying normal force, I'm saying normal stress diagram, right? So here, I go to the other one. The other one, same, except I divide this by this diameter, right? 8 divided by 2, 4, 10 to negative 3 squared. Then you get another axial stress. Now let's go to another example. 334.
that a roller, or is this supposed to be grounded?
That's a roller.
It's a roller.
Yeah, that's a roller. But this is connected to the roller through this bar, right? So when you have a force in it, you have a stress in it. The reason that I put roller here, because you don't put a moment or force in the X, it's perfectly on Y. And the cross section is, so the area of this is equal to 650 millimeter squared. The other one is 400. So it says find the value of X such that the stress, the normal stress in this column becomes equal to the tensile stress in this rod. So it says find X such that the stress here and here become equal. So what should I do? Pressing system. Then FPD. So my FPD is going to be, now how many force and moments do I have here? Just one. Upward. Let's call it, let's say this point, put some labels here. Let's say it's A and B. So that's going to be EY. And then you have a 3K here. And then you have AY for tension goes up. Right? I don't have X component, I don't have moment. Why do I don't have moment here? Because since there's roller, right? And there is no friction. So that's my FED. These are surface forces. Always check. See, go to the question, especially if your beam is made of concrete, if it's made of concrete and you see a beam, it's possibly it has some sort of body weight, dead load. Then you have to add that force at central, the gravitational force to the FED. But here we assume that the beam does not have the body force. So that's my FED. Now the next step is equations. So I write the moment, what A is equal to 0. That will give me 3K times this distance. Don't forget, from here to here, we can take it X. And you know X is not known. It's actually, there are no problem. We want to find X such that the stress here becomes equal to the stress here. So sigma A becomes sigma B. So X is unknown. So the moment about this A is 3K times X. Positive or negative? Negative. Then you go to the next one. EY times 200. Positive or negative? Positive. Look, you can convert that 200 to 0.2 to the meter. But if I consider my final solution as a millimeter, I'll just keep it millimeter. And this millimeter, you see, they cancel out from the solution. So it's just your choice. If you want to solve, I would recommend solve for meter. Meter for force Newton. If you have kilo, you just put 10 to 3. Although you can, sometimes you can save your amount of computation by not doing the writing. But I always recommend put the SI unit. If you have Newton, always use the SI units. So By times 200 positive. What else? That's all. Is equal to 0. Now I write one equation. I can say summation of force in Y direction, or I can say moment equation was B. Right? Let's do summation of force in Y. Summation of force in Y is equal to AY positive negative 3K plus BY. AY negative 3K plus BY is equal to 0. So all I need to do is to solve this equation. Other option was to write moment equation about B, and then you get AY with just one shot. You don't need to substitute this into that. But right now we need to first solve for By and then put it here to get Ay. So By is 3K times X divided by 200. Is By. And then you can put it here. Say Ay is equal to 3K negative By. 3K X over 200. Then you can factor out 3K, right? So what I did, 3K, you take it right, negative By. And By is 3K X over 200. So that's all you can solve. I have already used my three equations. What was the first equation? Summation of force makes 0. What kind of equation is that? It's a null equation. It's not going to help you, right? So I already used my summation of force Y and summation of moments. And I solved it. But look, can I solve, like, can I get decimal numbers for this? Can I get just using the equation of vector statics? Yes or no? Just without using the stress relation, just equation of vector statics. Can I get everything? No. So this is in fact statically indeterminate. Because what? Because how many unknowns did I have? 4. 3 equation, 4 unknown. You see? X is not solved yet. It's unknown. So what should I add? One additional equation, which call it the compatibility equation, in order to make the system compatible, so I can solve for everything. So what is the additional equation? The stress here is equal to the stress here. So how can I find the stress here? Put it cut here, and then say the force in this section divided by area in this section. What is the force in this section? The same Ay, right? So my additional equation, which I should add to that, is equal to, let's get to what is from the previous example. So you say additional equation is the stress here is equal to stress in this bar. That means that here is Ay divided by this area, 400 millimeter square is equal to the stress here, which is By divided by 650 millimeter square. Right? Of course, this cancels out with this, so you get a ratio. By is equal to multiply both sides by 650. 650 divided by 400. Dy is equal to 1.625 Ay. There you go. So how many equations do I have right now? If you divide Ay by By here, let's divide. You see here, this simply say By Ay is equal to 1.625. Right? Divide both sides by Ay. Right? Now this equation, what is your By? Your By is this divided by this one, Ay. So you get 3K times X divided by 200. This is your simply By divided by Ay. 3K minus 3K X divided by 200 is equal to 625. Now, how many equations do we have? One equation, one unknown for x. In fact, we were missing one equation, and we just simply add this equation of equality of the stress. And now I can solve for average. So how do we solve this equation? Well, first of all, let's get rid of 3k. Right? If you get rid of 3k, you factor out, so here, and then multiply by 200. So you get, the top becomes x, right? And the bottom becomes 200 minus x is equal to 200 times 1, 625. Right? So 3k cancel out with 3k here, so you get 1 minus x over 200, x over 200. And then you multiply by 200, then you get x, 200 minus x is equal to 200, 1 times 1, 625, right? Then you take this to the right, so you can say x is equal to 200
It's 325.
times 165, yeah, 325 times 200 minus x. And then if you solve for x, you get then you get 326 times x, which equals to 325 times 200. I don't think it's right.
Yeah, I don't,
We are missing something somewhere.
you added an extra 200 on the right side. When you multiplied the top and bottom by 200, you essentially multiplied by 1.
Oh yeah, thank you. I just, so the error that we had here, you know the reason that I found was mistake, you know how I found the mistake here? You see we have a step 1 verification. Remember? So I verified, I say, well, this should be somewhere here. Probably 150, 114. The one that I got was almost 200. So immediately I said there should be something wrong. Right? Now what was the problem? Here, when I multiplied top and bottom with 200, I must have multiplied the right side with 200. Somehow I did mistake, but everybody made mistake, so I apologize. So here, if I remove that, and if I do the calculus again, then I get x is equal to, then you multiply by 200 minus x, 1625 is equal to x. Then you get 123.8 millimeters. Double check my result because there may be still some amount here. So that means that at least that is in the range. So if this is 100, right, this tells me the load should be located right here. Let's see what. three single digits, 124. So the load must be here. So that's 124 milliliter. If you put the load here, the compressive stress or normal stress in both rods become exactly the same. So now, let's go solve more examples. Let's go, first of all, you may meet 2 quick bonuses. Two quick bonuses, okay? Did I apply your quick bonuses from the previous, already applied online? Another thing that we had from the previous semester, you see when I turn in your homework, some students don't figure out. And then it makes a huge confusion for me which one was which. So I may ask you guys, if you need your homework back, please come to my office instead of me bringing it for you. How about that? Do you think that's better? Instead of me bringing it here and everybody knows what's going on, you come to my office and pick it up.
You're talking about the quizzes, right? 'Cause the
Everything, quizzes, midterm, everything. But you see, this is the way I do it every semester. They come to my office and they check their work because we have more privacy instead of me doing it in the class. So you agree with that? I think everybody agrees with that. All right, so now let's go and do this, midterm waiver. Let's just do it today instead of leaving it to another day. In this case, this is one example of what I already discussed. You remember I said in value theorem in calculus, we say every non-uniform stress we can find an average, approximate average for that. So you say, yes, we have a parabolic, so that is y squared, if it is y. Somehow you have to find the function, this is force. And it's a parabolic profile, W squared. Somehow you have to find the function of that, and then based on the definition that we had, you find the average stress for this cross section. So what is this? This is like, for example, the beam. This is the beam that is fixed to the wall, and this is wall, and you have some sort of loading, and here you have parabolic near the load. And when you go far, then become uniform or constant. You see, it becomes constant. But near the load, you have parabolic case. Now, for this case, find the average stress. That means if you convert that to a constant average stress, let's call it sigma bar. Then what is that sigma bar? This was the formula I just wrote based on mean value theorem calculus. You know, you can do this, for example, roughly. You say, well, let's say everywhere I have 600 units. Although it's not right. You see, only at the center you have 600. And then it goes to 0, right? If you have 600 everywhere, then what is my average stress? No, let's say you have 600 everywhere. Is 600 divided by the area, which is 8 times, don't forget to convert this to meter, 10 to negative 3, right? And this is 600, this is already Newton, so it's in good shape. Newton meter squared, Pascal. So this is sigma average when you have everywhere 600. So this is the upper bound. But your actual thing that you get out of this integration should be smaller than that, right? So if you put this in calculator, the maximum becomes 600 divided by 6.25 megapascal. So what you get out of this integration, it must be smaller than that, because this is assuming that everywhere you have 600 Newton. This class is like, you remember vector statics, the first part of class was very boring. So please hang on to that. It's going to get interesting, I promise. Once you understand these basic things, and then we saw the actual structure, we can design it, and we can predict the failure when it breaks. So just try to don't go to sleep. I know that it's a very boring material, but it's going to get interesting. So what should I do? Well, this formula says the integral of this non-uniform profile over the area is equal to average stress times the area, right? So I can find average stress. Do I have area? Yes, right? So in order to take that integral, what do I need? Some sort of profile for sigma, some sort of function of sigma versus y, right? So what, I know that it's a parabolic, so I know that y is equal to ax square, ay squared, let's say sigma, force, this force, right?
Yeah.
F. F is equal to F of y dA, right? F is equal to something times y squared plus by plus c, parabolic. And the value of force is what? When you put 0, what do you get? Let's just put for y, put 0. You should get force is equal to 600 Newton. Then you say, if I put force 600, I get is equal to a times 0 squared, 0 plus b0, c. So my c is 600. Then I say at y is equal to positive 6, right here. You see this y0.
Yeah.
Positive 6 is here. If this is 12, then positive 6 is off, positive 6 is down. At y is equal to positive 6, what do I have? Force is 0. So put positive 6 here. So you have a times 36 plus b times 6 plus 600 is equal to 0. There's one equation. Then you have put negative 6. At negative 6, then you get negative 6 times a times, again 36, negative b times 6 plus 600 is equal to 0. And this is your curve equation. Just by applying this fact that this is 600 at the 0, 0 at the 6, 0 at negative 6. And the profile is parabolic, that means you have a square curve. Right? You can find all these constants. How many equations do you need? 3. 1, 2, 3. So if I add these two equations together, what do I get? 2 times, just add these two equations together. 2 times 36 times 8 plus 2 times 600 is equal to 0. That means your A is equal to 600 divided by negative 600 divided by 36. 16, negative 16, don't forget the positive negative one. 16 times 67. And then you can put it here and solve for B. And you get and B is equal to 0. Right? That means that your profile can be written, go back to this form. You can say F is equal to A, what A was, negative 16.67 y squared, B is 0 plus 600. That's your profile. Now put it here in this integral. Then you get sigma average times area, 12 times 8. 12 times 8, 10 to the negative 6 is equal to integral from negative 6 to 6 Fy, which is negative 16.67 y squared plus 600 dy times the depth, 8. So bring 8 here. 8 then to negative 3. So compute that integral, divided by this area, you get sigma bar. Now let's do, I don't want to say little labor, but 3 quiz bonuses. If you just solve this equation for sigma bar, what should I get? The maximum should be smaller than. So when you solve this equation, you should expect the number smaller than that. Right? Like this is the assumption that everywhere is 600. So in order to take that integral,
Is it 0? Is it 0? I think it's 0. That's what I got. Is it 0.4? I can both go to the same number.
look, this must not be 0. This is odd function. But the other one is constant. See, you have a constant function. This at least gives you 600 times 12. Right? This y is 6 minus 6, 12. At least for that. Now forget about the odd function. So just do it. You take this integral. You can put it in a calculator. Put this, you can put this formula or this one. Okay. Maybe it's right. It's wrong. Let me do it one more time.
That's what I have.
Maybe it's right. I don't know. Let me do it one more time.
The Casio has a integration function. That's what gets me. I got 4,799.
I got 400. That's what you do, the 40 divided by the area, 100%.
I did 4.
So you get 4.4 megapascal.
Yeah, that's.
You should get another say.
I'm with you.
You can tell me I'm wrong.
What did you get?
400,000.
Yeah, 400, this was of another unit, so this was 4, 7, 9, and then rounded up to 8.
You know what?
4,800, right?
Yeah.
Is that what you, so you multiply by that, and then you make it equal to sigma bar times 12 times 8 to negative 6. Then you solve for sigma bar.
So you get 400,000. Yeah.
4,800.
It's 5 Pascal, megapascals.
400.
Is it 4? It should be 2,400 miles.
Right? And it's not greater than that. That's a mega, right? So, is it to 10, 9, 10, or 15?
15.
15? No, 15. So, what we do here, I may give one of these integrals just for the heck of it, because the understanding the concept that when we say let's find the stress at this section, you always should consider that we have a variation at some section, especially near the load. Let's say this is your beam, and you have force here. Here is the point of the stress concentration. You have things like that. And when we get some special distance from here, then the specific one, which is L greater than 1, then you get uniform everywhere. Now let's solve one more example. We'll book maybe. This example is F711. And then we say find the stress at point B and A, and for example, the point B is C. So what should I do? First of all, in this case, you see these points are sufficiently far from the concentration point. Right? So your stress is, your profile is uniform. So you don't need to do the integration like that. This is just one case to show you that we can have advanced things like that. But for everything we do in this course, we assume that is uniform, constant. So at this point, I have a constant, sigma B, sigma at C, and sigma at A. So it say find these three expressions here. What should I do?
You just sigma is equal to force over.
Sigma is equal to force over area. The area is just so easy because the diameter is given for all the three sections. So what should I do? Force. So I have to find the axial load. You remember we talked about plot axial load diagram? Don't make the mistake when I say, you say, well, I have 3 kilo pound here, right, as press, it should be MB, right? And then therefore, this is 3K. Don't make this mistake. Why? Because between there, I have another 9 to the right. I have 3 here, 9 to the right. So this is not 3. Don't forget about these loads. So if you do that, if you draw it, so the first thing in this problem is draw the axiom. Also, this similar question is in your homework. Did you solve the homework or not?
Yeah.
Then what do you want to do with that? I think the problem was with the way I uploaded. I should go and enable the assignment, publish the assignment so you can see the calendar. So I extend it to the next week. I extend so you can do it too. Maybe not next week, maybe Friday. Good? Because I want to post another homework. So here, you have to draw the axial load. Diagram first. So here, yes, here is 3K, from here to here. But from here to here, you see you have a 9 and 3. 9 minus 3 is 6. And then you have some change here. The problem that the students have every time I post a question like that in quiz or midterm, they say, well, I have to, either they look at this end or this end. I have maybe 2 here, so it's 2 divided by cross-section area here. Don't forget about this load and this load.